Let's look at kinematic equations, or more commonly known as SUVAT equations. So these are the 5 kinematic equations, and we have a velocity time graph here of a particle which has an initial velocity of u, a final velocity of v, and the total time for its journey is t. Now on a velocity time graph, the acceleration, which we'll call a, is equal to the change in velocity over the change in time, which if we look at the graph in this case, we have an initial velocity of u and a final velocity of v. And so the change in velocity between the start and the end is v minus u. And then the change in time is the start time, which is at 0, and the end time, which is t. So this gives us t minus 0. And so if we simplify this, we end up with the acceleration, which equals to v minus u all over t. Now timesing both sides by t, we end up with at, which equals to v minus u. And then finally, if we add u to both sides, we end up with v equals u plus at, which is the first kinematic equation that we have here. We see that over here we have a trapezium, and so to work out the area of a trapezium, we have the area which equals to a half brackets a plus b times the perpendicular height h, where a and b are the 2 parallel sides of the trapezium. In this case, the 2 parallel sides are u and v, and then the perpendicular height is equal to t. In this case, the area represents the displacement, so we'll label this as S. Then we have the 2 parallel sides, which in this case are u and v, so we'll replace a and b with those. And then the perpendicular height of this trapezium is equal to t. We'll replace h with t, and this gives us our second kinematic equation. Using these 2 equations, we can now derive the rest of the kinematic equations here by eliminating each of the relevant variables. So to obtain the third kinematic equation here, we're going to eliminate v within this equation. And so to eliminate v, we're going to substitute in v equals u plus at. And so if we do that, we end up with s, which equals to a half brackets u, and now instead of writing v, we're going to write u plus at. So we have plus u plus at, and then close brackets, we have the t here on the end. Now if we simplify this, we end up with s equals a half, and now inside the brackets u plus u is 2u, and then we have plus at, and then close brackets, and then we have the t here. And now if we expand the brackets here, we end up with s, which equals to a half times 2u, which is u, and then a half times at, which is plus a half at, and then all of this now is being multiplied by the t here. And so if we expand the brackets again, we now get s equals ut plus a half times at squared. This is the third kinematic equation. To obtain the fourth kinematic equation, we need to eliminate u within this equation here. And to do that, we're going to use this first equation. So we have v equals u plus at, and we're now going to make u the subject by subtracting at from both sides. And so if we do that, we end up with u equals to v minus at. Now substituting this into this equation here, for u, we end up with s equals a half brackets, and now instead of writing u, we're going to write v minus at, and then we have plus v, and then close brackets, and now we have t on the end. And so simplifying this, we end up with a half brackets, now v plus v is 2v minus at, close brackets, and then we have the t on the outside. Now expanding the brackets here, we end up with s equals a half times 2v, which is v, and then a half times minus at, which is minus a half at, and then all of this is in brackets, and we now need to multiply by t here. And so we now end up with s equals v times t, which is vt, and then minus a half at times t, which is minus a half at squared. And that is the fourth kinematic equation here. Finally, for the last kinematic equation here, we see that there are no t's involved. And so we're going to start off with the first equation, and we're going to make t the subject. And so if we do that, we end up with v equals u plus at. And now rearranging to make t the subject, we first take away u from both sides, which gives us v minus u equals to at. And then we divide both sides by a, which gives us v minus u all over a, which equals to t. We can now substitute this into the second equation here. And so we end up with s equals a half brackets u plus v. And now instead of writing t, we're going to replace that with v minus u all over a. And so we'll add this in brackets as v minus u all over a. Now we can times both sides by 2 to get rid of the half here. So we end up with 2 times s, which is 2s, then 2 times the right hand side cancels with the half, which leaves us with u plus v in brackets, and then we have v minus u all over a. Similarly, to get rid of this a here in the denominator, we can times both sides by a. And so if we do that, we now end up with 2s times a, which is 2as, and then on the right hand side we have u plus v in brackets, and then in our second bracket we now have v minus u, since multiplying by a cancels with dividing by a here. If we now expand the brackets on the right hand side out, we end up with 2as, and now we have u times v, which is uv, u times minus u, which is minus u squared, v times v, which is v squared, and then v times minus u, which is minus vu, or we can write that as minus uv. And now simplifying this, we end up with 2as equals to, now uv minus uv cancels, and so we're left with minus u squared plus v squared, which can be written as v squared minus u squared. And so finally, if we add u squared to both sides, we end up with v squared, which equals to u squared plus 2as. And this is the final kinematic equation. So that is how you derive the 5 kinematic equations, where s is the displacement, u is the initial velocity, v is the final velocity, a is the acceleration, and t is the time. And hence, these are commonly known as the SUVAT equations.